Okay. So complex numbers. I know you've had this before. So a lot of the mechanics will be the same. I will probably set it up a little different than other teachers do. Tell you, unless you've been in my class before, some of you, you've heard it already. But just remember that we got a lot of ways to solve equations, including graphing. And I'm showing quadratics specifically, but it could be anything. And solving equations by graphing means here's the equation, right? It has an answer that we could solve for. We solve it by turning it into a function, by making the 0 into a y, right? So now it's got two variables, which you can't solve, but you can plot the points and see the shape of the graph. And then you can look for the place on the graph where y equals 0, that'll be your answer. And where does y equal 0? On the graph, on the x-axis. So you look for where does it cross? Those are your answers. So for this parabola, it's quadratic. We expect two answers, and we can see them both on the graph. They're both real numbers. Okay. Right. Did somebody need to? Okay. Okay, here'd be an example of one that when you graph the function and you look for the x-intercepts, it actually touches the x-axis and then it goes back, which we've already experienced this, right, when we graphed. And that's just telling you that the factor x minus 1 is there twice. But there's actually one more situation, which is it doesn't cross the axis at all. Right? And when that happens, it's not that it doesn't have any answers. It's just that the answers are not real numbers. Right? They're another kind of number, which has the unfortunate name of imaginary. And it's unfortunate because it makes you think like you're just doing this stuff for practice, for as an amusement or something, that it's not real in a sense. But it is real. And this is the story, which I'll bore you with, that if you've been in my class before. When I was getting my bachelor's in meteorology at Penn State, and we were in a class which is called micrometeorology, which had to do with the energy balance of the sun and the earth and the atmosphere and all that. And what we were studying specifically was, we know that the atmosphere is transparent to sunlight. The wavelengths are too short. So the sun doesn't warm the air as it hits the atmosphere. If it did, it would be warmer up there and colder down here. In fact, it shines all the way through, gets absorbed by the earth, and then the earth re-radiates at longer wavelengths, which are absorbed by the atmosphere. That's why it's warmer down here, right? Also, ideal gas laws and things like that. So it takes a little time for that process to happen. And we're trying to figure out, well, how long does it take for that? I mean, we know instinctively that when we get the most sunshine, like 12 o'clock noon, that is not the time when it's the warmest. So there's something going on there. So we model the situation with math, that the equations that end up being used are partial differential equations, the kind of things that you wouldn't get until you go from here to about 3 or 4 courses down the road in calculus. And the solutions involved imaginary numbers, these same things that we're doing today. In fact, they involve, you end up getting solutions which are e to the I x. And e is the base of the natural logarithm. It's an exponential function. And whenever you get the e to the ix, that gets broken down into cosine x plus I sine x, which is informative because we know what the shapes of sines and cosines are, right? They're waves. And when you're trying to model temperature, which goes up and then goes down and goes up and goes down, it's kind of nice that our models seem to be breaking into a pattern that looks like it might work. Okay. So we ended up using partial differential equations, getting solutions which involved imaginary numbers and developed waves. And what we discovered was, or what our model told us, was that you should expect the warmest temperatures 1/8 of a cycle after the most sunshine. So if you take on a daily basis, at what time of day do we get the most sunshine? When is the sun most directly overhead? Noon. And in summertime, 1 o'clock is daylight savings time. Okay, what is 1/8 of a day? 3 hours, right? So now, if you add 3 hours to noon or 1 o'clock in the summer, that means your high temperature should be around 3 or 4 o'clock. Does that seem reasonable? It is. Take it on an annual basis, right? When do we get the most sunshine during the year? Meaning which day's the longest of the whole year? June 21st, okay? Is that when we get the hottest temperatures of the season? No. Okay, what's 1/8 of a year? Take it in months, right? There's 12 months divided by 8. Be 1.5, right? Or about 6 weeks. So go from June 21st, about 6 weeks later, end of July, beginning of August. Does that seem like when we get the hottest temperatures? It does. So, I mean, this is not always the case that you model a real-world situation and you get something that just squares with your intuition so well. A lot of times you run your model and say, didn't work. Back to the drawing board. But that one wasn't. That was one that worked, actually. And it's just to show you that these things we may call them imaginary, but they have practical uses. They really do. That's why we learn about them. Okay. Now we can get on to the basics. Imaginary numbers. Right? Imaginary numbers to us mean the letter I, right? The lowercase letter I, which we define as the square root of -1. Right? That is a definition. Okay. Now, if you square both sides of that statement, then you get -1 equals I squared. So a lot of times in our calculations, that's a substitution we have to make. Whenever you make an I squared, you substitute -1. Right? That's important to know. You ready, Courtney? Everybody? All right. So now, the imaginary numbers, when you put them together with the real numbers, right, those are mutually exclusive. They make up what we call complex numbers. We usually kind of think that real numbers is the big set of numbers. It's not the big set of numbers. The big set of numbers are complex numbers because they include some numbers that are not real and they include the real numbers. Okay. The standard form of a complex number is A plus BI, where A and B are real numbers. Right? So basically you've got two terms. The first term is a real number. The second term, because it's multiplied times I, is imaginary. Right? So you add those up, that's a complex number. Right? The real numbers are a subset of the complex numbers. They are the particular case when the B equals 0, there is no I. Then it's all real. Okay? When the B does not equal 0, then you got an I, then it's imaginary. Good, Chen. Janine. Good. Slow me down if I'm going too fast. Jimmy, you ready? So we'll do a bunch of things. We'll add, subtract, multiply, in a sense divide, solve a little bit of equations that end up having imaginary solutions. But first we just talk about what does it mean for two imaginary numbers or complex numbers to be equal. Right? So if you have two complex numbers, and I'm using this in the most general sense, right? A plus BI equals C plus DI. In order for the complex numbers to be equal, it's got to be that the real parts are equal, A equals C, and the imaginary parts are equal, B equals D. That's what it means for two complex numbers to be equal. So, and you have two homework problems like this. if you say a plus bi equals 13 plus 4i, then you should be able to say what are the a and the b, right? Because you're going to make an equation, an equality out of the real parts and the imaginary parts. What does a equal? A equals 13, right? And what does b equal? 4. But sometimes to make these problems more interesting, there's actually a little bit of calculation you've got to do. So here, a plus 6 in parentheses, that's the real part, plus 2b times I, that's the imaginary part, equals 6 minus 5i, right? How can I set up an equation that I can solve to know the real part here? Basically, these things usually you're solving for a and b to make these equal. What should I say about the real parts? A plus 6 equals 6, right? The real parts must be equal. So if a plus 6 equals 6, then a equals 0. All right, and what equation will we set up for the imaginary parts? 2b equals negative 5, right? Just that. So if 2b equals negative 5, then b equals negative 5 over 2. Right. So just trying to get at, in order to have real complex numbers be equal, their real parts have to be equal, their imaginary parts have to be equal. Oh, that's right. Okay. So good. Okay, adding and subtracting complex numbers. Again, I've got the abstract, definition of it here, and then some examples down below. If you add complex numbers, you add the real parts, you add the imaginary parts, right? If you subtract the real parts, you subtract the imaginary parts. So 7 plus 3i plus 5 minus 4i, add the real parts. What do you get? 7 plus 5 equals, come on, 12. Add the imaginary parts. 3i minus 4i, or plus a negative, negative I. Right. Add the real parts, add the imaginary parts. Even like the next one, which has actually got 3 complex numbers, you still combine the real parts, combine the imaginary parts, right? And take into account the fact that there's actually a plus here and a minus there. And a minus in front of parentheses is going to distribute to all the terms. So let's see, what will the real part be of our answer here? 5 plus 3 minus 8 is 0. Right. How about the imaginary part? How many i's do we have if it's negative 3i plus 5i plus 2i? Negative 3 plus 5 plus 2. Oh, actually, I'm wrong, aren't I? It's actually negative 3 plus 5 minus 2, which is 0. So it's actually 0 plus 0i, which is 0. I knew those canceled out. Which tells you what? We added imaginary numbers, and what kind of answer did we get? A real number, right? So you can add imaginary numbers. I mean, I don't know if you ever talked about it much. It's one of the properties that's in the beginning of the Algebra 2 book called closure. That if you do an operation, if I add real numbers, I always get a real number, right? But obviously when I add imaginary numbers, I don't always get an imaginary number. So we don't have the property of closure for imaginary numbers. Not for addition and subtraction, as we just saw. Yeah. here, there's a minus in front. We good, Courtney? Okay. When you multiply complex numbers, well, take it in its, if you've got a real part and an imaginary part of both, it's multiplying binomials, right? And we have a process for that, which is, how do we multiply two things times two things? FOIL. I mean, if you don't call it FOIL, that's fine. I know some teachers act like that's beneath them to call it FOIL, but I don't have a problem with it. FOIL it. Right? So the first terms, right? 2 times 3, 6. The outer terms, 2 times 3i, 6i. The inner term, 3 times negative 4i. And the last terms are negative 4i times positive 3i. Let me write that out. Negative 4i times positive 3i. Okay, so that's going to be negative, right? 4 times 3 is 12. And then I times I is I squared. But what does I squared equal? Negative 1. So whenever you make the I squared through multiplication, then you're going to substitute negative 1. So this whole last term equals 12. So now we can simplify. We add the real parts. 6 plus 12 is 18. 6i minus 12i minus 6i. How about the 4 plus 2i squared? How will we do that? Pierce? Say again? You're going to have to FOIL it, right? Don't look at it like 16 plus 2i squared, right? It's up 4 plus 2i times 4 plus 2i, right? So whatever's in parentheses times itself. So 4 plus 2i times 4 plus 2i. And that's a FOIL. 16 plus 8i plus 8i. And then the last term will be 2i times 2i, right? It'll be plus times plus. 2 times 2 is 4, and then it's an I squared. But I squared is negative 1. So this is actually 16 plus 8i plus 8i minus 4, which is 12 plus 16i. I got 3 slides to go. Short. Okay. Now, when complex numbers differ only by the sign in between the real part and the imaginary part, those are called complex conjugates. A plus bi, a minus bi. Complex conjugates. So let's see what happens when we multiply complex conjugates. Right? We'll FOIL it. Right, the first will be 4 times 4. Come on. Because I leaned on there. 4 times 4 is 16. 4 times negative 5i is minus 20i. Then the inner is 4 times positive 5i, which is plus 20i. And the last will be 5 times negative 5 is minus, it's 5 times 5 is 25. And it's I times I, which is I squared. So the middle terms cancel, and they always will with complex numbers. When you multiply complex conjugates, the middle terms cancel. Okay, and the last term, because it's got an I squared in it, you substitute -1. So what is -25? I squared plus 25, right? Which is plus 25. So what happened is 16 plus 25 is 41. Again, we went from two imaginary numbers to a real number. No more I. And that always happens when you multiply conjugates. Okay, good, 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 Jimmy, good. So that leads to the strategy for what they don't call it division. What they say is simplify the quotients of complex numbers so that the result is a complex number in standard form, a plus bi. Basically, we're going to turn the denominator into a real number by multiplying it by its complex conjugate. Not the numerator's complex conjugate, but what is the complex conjugate of 4 minus 2i? 4 plus 2i, right? So we're going to multiply the denominator, 4 plus 2i, and then because of basic algebra, right, if we're going to do the denominator by 4 plus 2i, we got to do the numerator times 4 plus 2i. Right, that's the strategy. Multiply by the conjugate of the denominator over itself. Now, see what happens. In the numerator, it's a FOIL. So 2 times 4 is 8. 2 times 2i is 4i. 4 times 3i is 12i. And 3i times 2i is 6i squared. And when we do the denominator, okay, you could think of it like a FOIL, but the middle terms, the O and the I, are going to cancel each other out. So all you really need to do are the first terms and the last terms. 4 times 4 is 16, and negative 2i times positive 2i will be negative 4i squared. Right. Now, in the numerator, this 6i squared it's minus 6, right? So 8 minus 6 is 2. 4i plus 12i is 16i. In the denominator, minus 4i squared becomes plus 4, right? So that's over 20. Right? And you could think of that like that's 2 over 20 plus 16i over 20, and then simplify both parts of it. This will be the a plus bi. 1 over 10 plus 4 over 5 times I. Good. Okay, which leads to now we can solve equations and not stop just because all the answers are not real numbers. Now, usually when you get a quadratic equation to solve, in your mind you're thinking, first, is it factorable? And 8 times 9 is 72. Are there factors of 72 that add up to 14? The answer is no, it's not factorable. Second, you could solve it by graphing, but if it doesn't cross the x-axis, that won't work. You could solve it by completing the square, but completing the square is a process which is essentially the quadratic formula. The one method you can always count on is quadratic formula. So let's do quadratic formula with this right here. right? And again, the quadratic formula, which we should know, but okay, so here I go. Negative 14 plus or minus the square root of 14 squared minus 4 times 8 times 9 divided by 2 times 8. Negative 14 plus or minus, okay, 14 squared is 196. 72 times 4, 288. So 196 minus 288 should be negative 92. So we're taking the square root of a negative number. That's where the imaginary number comes up, right? And in the denominator, we have 16. Now, 92 is not a perfect square. Can you think of any factors of 92 that are? How about 4? You know, it's divisible by 4. 4 times 23 is 92. So let's see. If I do 92, I'll say negative 92. Negative 4 times 23. 23 can't be simplified any more than that. So we're going to take the square root of 92, and instead we'll do the square root of negative 4 times the square root of 23, which is 2i times the square root of 23. Right? When we take the square root of 4, we get a 2. When we take the square root of negative 1, we get I. So we're going to replace that. That's negative 14 plus or minus 2i times the square root of 23 all over 16. Okay. And then any more simplifying you could do? Yeah? I mean, again, looking at these numbers, not any number in the radical, that would not count. But 2, 14, 16 are all divisible by 2. So you should factor out a 2. Negative 7 plus or minus I times the square root of 23 divided by 8. Now, I think it comes up a little bit later. Maybe it's in the next section or something like that. We're going to get a theorem which says that if ever you get a solution to a problem that's an imaginary number, there must be the complex conjugate also. And that's because of this. Because where do our imaginary solutions come from? They come from the quadratic formula, right? Where does the I come from specifically? It comes from that square root. And you would never just have the plus. You would always have the minus too. So you're never going to get one of these as an answer. You're always going to get a pair, right? The plus and the minus here, those are conjugates. Because that's the only difference between conjugates is the sign in between. So you always get imaginary numbers in conjugate pairs like that. And for that matter, if you get a square root in your answer, it's the same thing. The square root came from there. So you always get square roots in conjugate pairs, like 2 plus the square root of 3, 2 minus the square root of 3. It has to, because that's where it came from. Okay. That is everything you need to know about imaginary numbers. And there's a lot of problems, but they're mostly just basic stuff that I think you'll blow through really quickly. I think you'll probably be like way into here by the time you leave, even if with a quiz to take.